Hey there, everyone. Let's take a look at Summary Time version 2. We did one of these last semester, but I've modified this one a little bit to include some extra stuff from that wasn't included in the first one. So let's go through it. Um, f of x equals negative x squared has a maximum at x equals 0. So think about that graph. It sure does. And so my justification would be f has a max at x equals 0 because to the left of x equals 0, f prime is greater than 0, increasing, and to the right of x equals 0, f prime is less than 0. Slopes are negative here, f is decreasing. Okay, f has a minimum at 1, write a justification for this minimum. Okay, so let's take a look at the little graph here, negative x plus 1, and then there we do have a minimum there. And so f has a minimum at x equals 1 because f prime is less than 0 to the left of x equals 1, decreasing on f, negative slopes on f there, so f prime is less than 0, and f prime is greater than 0, f is increasing because of these positive slopes to the right of x equals 1. Okay, f of x is this function, has a maximum at 2. I'm going to graph this function. Thank goodness I know about my transformations. I shifted right and flipped upside down. And surely I have a maximum there, and that's a left endpoint. So this is the left endpoint max justification. There is a max at x equals 2 because x equals 2 is the left endpoint, and to the right of x equals 2, f prime is less than 0. I have all these negative slopes here, so f must be decreasing. This function has a minimum at x equals 2. It sure does, and again, that's a left endpoint. So we're going to say there is a min on f at x equals 2 because x equals 2 is the left endpoint, and to the right of x equals 2, f prime is greater than 0. All right, where can you find maxes? F prime equals 0, f prime undefined, and endpoints. How do you know, how do you know what the value of a min-max is opposed to where it occurs? You plug the where the max min x value is into the original function. So we're using the derivative to find the max of min, but then we're going to take that critical number, or that endpoint, and plug that into the original function. How do you know where f of x is increasing or decreasing? F is increasing when f prime is greater than 0. F is decreasing when is less than 0. Okay. What is the justification you write to explain when a function is increasing or decreasing? F is increasing on a to b because f prime is greater than 0 on a to b. How do you know when f is concave up or concave down using f double prime? F is concave up when f double prime greater than 0. F is concave down when f double prime is less than 0. What justification would you use to defend when a function is concave up or concave down by using f prime, double prime? F double prime, f is concave up on f double prime, no, on a to b because f double prime is greater than 0 on a to b. F is concave down on a to b because f double prime is less than 0 on a to b. How do you know when f of x is concave up or concave down using f prime? So f is concave up when f prime is increasing. That's the slopes increasing, the slopes of f prime. So the slopes of f prime, increasing slopes, I need positive f double prime. I need positive slopes for increasing. F is concave down when f prime is decreasing. What justifications do you write? F is concave up on a to b because f prime is increasing on a to b. F is concave down on a to b because f prime is decreasing on a to b. And usually I use this one when I'm looking at a graph and I see they give me a graph of f prime and I look and I say, oh look, f prime is decreasing on that interval. How do you find inflection points in f of x? Well, I can do it one of two ways. I find inflection points on f are maxes and mins, but not endpoint maxes and mins. On are maxes and mins on f prime, or where f double prime changes sign from plus to minus or minus to plus. You could just say changes sign for that one. What justification would you write to justify an inflection point at x equals a using f double prime of x? Okay, so f has an inflection point at x equals a because f double prime changes sign at x equals a. Next, write the justification using f prime at x equals b. F has an inflection point at x equals b because f prime goes from increasing to decreasing or decreasing to increasing at x equals b. How can you use f prime and f double prime to determine whether there's a max at x equals a on f of x? Okay, so this is our second derivative test. If f prime of x equals 0, I think this works for undefined as well. And but let's just go with f prime equals 0 and f double prime is greater than 0, then I'm looking at a situation like this, and therefore there is a min at x equals a. If f prime of a equals 0 and f double prime of a is less than 0, I'm looking at a situation like this, in which case, therefore, I have a max at x equals a. So I'm looking at two things. I want to determine when f prime is equal to 0 and if f double prime is positive or negative. To determine positive means I have a min, negative f double prime means I'm going to have a max. Okay. When looking at the graph of f, how do we know about f when f prime, or what do we know about f when f prime is above the x-axis or below the x-axis? If f prime is above the x-axis, f is increasing. If f prime is below the x-axis, then f is decreasing. When f prime is increasing, what does that tell you about f double prime? So if f prime is increasing, f prime has positive slopes, therefore f double prime is greater than 0. And since f double prime is greater than 0, we know that f is concave up. When f prime is decreasing, what does that tell you? Well, if f prime is decreasing, that means f prime has negative slopes. Therefore, f double prime would be less than 0. And what does that tell me about f of x? Therefore, f of x is concave down. Okay. Is it possible to have neither a min at max or max at f prime equal to 0? Sure. If we look at this y equals x to the third graph at x equals 0, we have a horizontal tangent here, but we have neither a min nor a max. Oh, and include a picture. So we have neither a min or a max. I believe this would be, is always going to be the situation, an inflection point on f, where f prime was equal to 0, but we didn't have a min or a max. But we can certainly have this situation occur. Okay, is it possible to have an inflection point where f double prime is undefined? Well, that's an interesting question, and we talked about shark fin. The second derivative is undefined at this point, but I went from concave down to concave up, and so I would argue that this is an inflection point because f changes concavity at this point. So the first derivative and second derivative won't exist. They'd be undefined at this point, but I have a change in concavity at this point. Is it possible to have an inflection point at an endpoint? No. You need a change in sign to have an inflection point. So if this is my endpoint and I've got positive over here on f double prime, do I know whether I'm negative over here? Maybe positive, maybe 0. Look, I have no idea. There's no sign change here. So an endpoint can be never an inflection point. Okay, some fill-ins. If f prime is greater than 0, then f double prime is positive. If f prime is less than 0, then f prime is negative, or f double prime is negative. If f double prime is positive, then f is concave up, and f prime is increasing. If f double prime is less than 0, then f is concave down, and f prime is decreasing. F is increasing, then f prime is positive. F is decreasing, then f prime is negative. F prime increasing means that f double prime is positive, and therefore f is concave up. F prime decreasing means that f double prime is negative, and therefore f is concave down. Okay, what can we say is happening at x equals c in each of these situations? Here's an f prime sign chart. We've got a max here. We've got a min here. We have a horizontal tangent, but no max or min. What can we say is happening to the left and right of x equals c in each situation? Okay, so let's call this one Roman numeral 1, Roman numeral 2, Roman numeral 3. Roman numeral 1, to the left of x equals c, f is increasing because f prime is greater than 0. To the right of x equals c, f is decreasing because f prime is less than 0. Roman numeral 2, to the left of x equals c, f is decreasing because f prime is less than 0. To the right of x equals c, f is increasing because f prime is greater than 0. And finally, Roman numeral 3, f is to the left of x equals c, f is decreasing because f prime is less than 0, and to the right of x equals c, f is decreasing because f prime is less than 0. What can we say is happening at each of those? Well, I see f is increasing, so f double prime is positive, which means that therefore f is concave up. And here f prime is decreasing, so f double prime is less than 0, therefore f is concave down. And so I want to say whoa, increasing, decreasing. What's happening? So f of c is an inflection point. F prime of c is, I went from increasing to decreasing, is a max, and f double prime of c is equal to 0, because I went from positive f double prime values to negative f double prime values. Oh, that was a very interesting question. And here things have flipped. I still have that change in concavity. So f of c is still an inflection point, and f double prime of c is still going to be 0, but f prime at c isn't going to be a max anymore, going from increasing to decreasing. I'm now going from decreasing to increasing, and so I have a min. What can we say is happening to the left and right of x equals c on f of x and f in each case above? I thought I said that. Oh no, I guess this is more about concavity. To the left and right. Okay, so Roman numeral 1, to the left of x equals c, f is concave up, and f double prime is greater than 0. To the right of x equals c, f is concave down, and f double prime is less than 0. Roman numeral 2, those things are going to be switched. We're going to say to the left of x equals c, f is concave down, and f double prime is less than 0, and to the right of x equals c, f is concave up, and f double prime is greater than 0. We know that f is concave up because the second derivative is greater than 0. We know the second derivative is greater than 0 because the first derivative is increasing. That means the first derivative has positive slopes. The slopes of f prime are positive, therefore f double prime, the slopes of f prime would be positive. Okay, next. What can you say is happening at each situation above at x equals c? F prime is positive, so the function is increasing until we get to say, so we have a max at x equals c on f. Now I have an endpoint here and a minus, so I'm decreasing from that point. Hey, so there's also a max at x equals c on f. Here, my endpoint is on the left, and from there, f is increasing, so we have a min at x equals c on f. And then here, we're decreasing until we get to c on f, and so there's a min at x equals c on f. Fill in the table. Okay, what do we know? Just because f is positive or negative, I have no idea what's happening for increasing, decreasing, or concavity. Now, if f is increasing, I know that f prime is positive, but I have no idea whether I'm increasing this way, or this way, and so I don't know that one. If f is decreasing, then f prime is negative. And again, I don't know if I'm decreasing this way, or this way, or this way, so I don't know anything about concavity. Now, if f prime is increasing, then f double prime is positive, and therefore f is concave up. And if f prime is decreasing, f double prime would be negative, and therefore f would be concave down. Okay, only a page and a half to go. V equals dx dt tells us that velocity is the rate of change in position with respect to time. This means instantaneous velocity at x equals a would be v of a, or x prime of a. The average velocity, yes, but what's speed? Define speed in terms of velocity. Oh, speed is the absolute value of velocity. Hey, and remember, if we integrate absolute value of velocity from A to B, we get total distance traveled on A to B. Okay. How do you know when speed is increasing? How do you know when speed is decreasing? Speed is increasing when velocity and acceleration have the same sign. Speed is decreasing when velocity and acceleration have opposite signs. Okay, tell the signs of the first and second derivative if you know the following. F is increasing at an increasing rate, so f prime is greater than 0, and at an increasing rate, f double prime must be greater than 0. F is increasing but at a decreasing rate, something that looks like this. So f prime is greater than 0, and f double prime, because concave down, increasing at a decreasing rate. F is decreasing at an increasing rate. Decreasing at an increasing rate looks like this. So f prime would be less than 0, and f double prime would be also less than 0. And now I want f is decreasing at a decreasing rate. That's this one. Now, many students think that this one, decreasing at a decreasing rate, is this picture. But think here, we have a slope of negative 100, and then a slope of negative 10, and then a slope of negative 1. Oh, I really did flip them, didn't I? These numbers are increasing. Oopsie. We're going to switch these two. Um, so f prime in this case, decreasing at a decreasing rate. Decreasing. No, these numbers are, yeah, these numbers are increasing. These numbers are decreasing. And so we need to switch these. These values need to go over here. And here we need to say f prime would be less than 0, but f double prime would be greater than 0. This is that one, and this is that one. See, a lot of people make that mistake, including me. What do we know about f prime in each of the following cases? Increasing at an increasing rate. We know that f prime is greater than 0 and f prime is increasing. F prime is increasing at f is increasing at a decreasing rate. So f prime is greater than 0 because f prime is increasing, and f double prime, and f prime is decreasing. F is decreasing at an increasing rate. F prime is less than 0. F double prime is greater than 0. And F is decreasing at a decreasing rate. Okay. And then on the last page, explain IVT to your parents, include diagrams, an example, and words for your explanation. Well, remember, we really need to stress the preconditions. If f is continuous on a to b, we need to establish that first. Then f must pass through all values, and those are function or y values, from f of a to f of b. So a f of a, b f of b. We're going to pass through all these y values, and this is most often used to say, hey, if this is less than 0 and this is greater than 0, then there must be a 0 or x-intercept on the interval from a to b. Okay, and then MVT. Well, let's take a look at MVT. So with MVT, we've got two preconditions. If f is continuous on the closed interval a to b and differentiable on the open interval from a to b. We need to address these when we're doing MVT problems with the AP exam. Then what must be true? Then there must be at least one point x equals c such that f prime at that point, the slope at that point, is equal to the average rate of change minus, or the slope of the secant from a to b on f of x. And so what we're saying is if we have this situation and we have this average rate of change here, because this function f is continuous on this closed interval from a to b, and there's everywhere differentiable here, there must be at least one point, x equals c, where the slope of the curve is equal to the slope of the secant. And in this case, I see one I see 2. But I'm guaranteed at least one place when when I've met these preconditions, where the slope of the secant, the average rate of change, is equal to the slope of the tangent, or the instantaneous rate of change. Okay, well, I hope that helped you. Have a wonderful day, everyone.